Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to describe simple circuits, a little bit about how they work, and to introduce a topic called EMF. Alright, so we have a picture here that we're looking at right here of our very simple circuit here. It has some sort of voltage source, right, which in this case is going to be a battery. It's running a light bulb, and like all circuits should have, it's, got a switch to turn it on or off. In the case we have it shown here, it's turned on. So the first thing to discuss here are these arrows. So the arrows in this picture here, here, and here, these represent currents, which is movement of charge carriers. Now, this is the positive terminal of the battery, which means it's going to attract electrons. So the arrows shown are in the actual direction of electron motion. So overall, the free traveling electrons in this wire are moving counterclockwise. Electrical current, however, it is generally standard sign convention to assume positive charge carriers. And I always say this with a smile because we know that in circuits, we know that the actual charge carriers are electrons. But I'm going to go ahead and make this modification here, assuming positive charge carriers. Get rid of these arrows. And therefore the positive current direction is this way. Now let's put a few of these arrows here. Very important to note, this is a single current or single loop here, and the current is the same everywhere. It has to be in this circuit. Okay, next up here. So the battery itself, or I'm sorry, not the battery, the light bulb itself here is a source of resistance in the circuit. You know, if I were to take a wire and just kind of jump this would be shorted out and the current would spike. All right, so the light bulb itself has got some internal resistance. Just a little reminder about resistance. Here's the symbol for it. That's called an ohm, which remember is a volt per amp. Resistance is perfectly named. You know, if you had something with a resistance of 10 ohms, that means it takes 10 volts to get a 1 amp current. If you had 100 ohms, it would take 100 volts to get a 1 amp current. See, more resistance. All right, the next thing I want to discuss here is the battery. So the batteries have a voltage source, and if I were to take a voltmeter and we were to put leads here, whoops, I wanted to do that in red, here, and the other one over here somewhere. All right, what you'll find is that the voltage that it reads will change when the switch is closed. With the switch open, you'll get a certain number here, and I'm just going to make up an example. Let's say, maybe something like 1.6 volts. And then when you close the switch, it's very common to watch that voltage drop, maybe to something like 1.4 volts. So you really have kind of two different voltages to talk about. There's what's called open circuit voltage, that would be this one in my example, and closed circuit voltage, which is this one. Now the reason the voltage drops is because the batteries itself, has some internal resistance to it. So this battery right here, it has a little bit of internal resistance. I'm going to call that little r. So when you run a current through it, you get a voltage drop across the leads. All right, so when you draw a circuit picture, which I'm going to do next here, you typically would model the battery here as a voltage, which is what's called the open circuit voltage, with a resistance to it. So this, a voltage source and a resistor, is how we typically would model this in a circuit. All right, so this open circuit voltage here has a special name. Right? I'm just going to put open circuit voltage. I don't feel like writing that out. It's also called EMF, which stands for Electromotive Force. This is one of the worst named things in all of physics because it's not a force. It's not a vector, and it doesn't have units of newtons. EMF has the same units as electric potential, and it's defined in a very similar way. So electric potential is defined as potential energy per unit charge. Well, EMF is defined as work per unit charge. So it would have units of joules per coulomb or volts, just like electric potential. So we like to, when you're modeling a battery here, you think of it as an EMF with an internal resistance. All right, the rest of the picture, we got the wire, and we would typically replace the light bulb with a resistor. Circuit symbol for a switch looks like this. Okay. With the switch open, there would be no voltage across the resistor, and my voltmeter here across the battery would read the EMF of the battery, the open circuit voltage. With the switch closed, in our picture we would now have a current this direction. Over here it would be this way, over here this way, over here this way, and again the current in a single loop, this is a single loop, has to be the same everywhere. I'm going to make a completely separate video on why that is. And now we would have a voltage drop here, a small little delta V by an amount IR. So now our voltmeter over here, if we had the leads here and here, is going to read the EMF minus IR. Now, I think I've gotten about as far in this video as I really want to get to. Some important things here. Circuit symbols, or this is the symbol for resistance. Batteries have what's called an open circuit voltage, and we typically model a battery, like in a picture, as an open circuit voltage with an internal resistance. Currents are generally drawn assuming positive charge carriers, we always say with a smile. And I think that's about all I want to talk about for this particular video. So I hope that this has been at least an interesting introduction into simple circuits. Have a great day.